Welcome back to Calculus 2. In this section, we're finally going to talk about our first test for convergence. We already had a test for divergence, the nth term test in the last section. This is going to be our first test that will also, could possibly, show convergence. First, we're going to look at this corollary of the monotonic sequence theorem from 10.1. It says a series of non-negative terms converges if and only if its partial sums are bounded from above. So, if you're not familiar with some discrete math, if and only if statements mean if this, then this, if this, then this. They have to go an if-then both ways. So it's actually kind of two proofs involved in doing it. You have to show assuming the first term results in the second, and then you have to assume the second and show that results in the first. But this is pretty simple in both ways. Most corollaries are. That's why they're called corollaries. They naturally follow. So, if you assume the partial sums are bounded from above, then I figured I'd show you the monotonic sequence theorem. If a sequence is bounded and monotonic, then the sequence converges. Bounded and monotonic just means it's bounded above and below. We already know it's bounded above because that's given in the statement. Also, it's bounded from below because they're non-negative, so it's bounded by 0. So just by that, the sequence of partial sums has to converge by the monotonic sequence theorem. Going the other way, if the series converges, it converges to some number s, where s is some positive number, but that number s happens to be an upper bound, because if it weren't, eventually you'd get some partial sum that was greater than it, and you'd never be able to go back down towards s, because there's no negative term. Each additional term you add on would just push it farther away from the limit. So it has to be always underneath, but approaching. It can't ever cross s. So there you go. That's the proof. Now let's get the big one, the integral test. So if you have a sequence of positive terms, a sub n, and the formula for the sequence equals the formula of a function that is continuous, positive, and decreasing for all x greater than or equals some positive integer, then the series, n equal capital N to infinity, basically the tail of the series, and the integral from capital N to infinity, both converge or diverge. So wherever the series actually matches up with the function, if you can calculate the integral of that function from n to infinity, and it's finite, it converges, the series has to converge as well, and vice versa. If this diverges, the series has to diverge as well. So it allows you to test some series just by doing some integration. It does have a pretty restrictive set of conditions, continuous, positive, decreasing, but it's still a very useful test. If for no other reason than to establish a bunch of functions we can maybe do comparison tests with later when we get into comparison tests in the next section. So let's prove this. So suppose we have a function that looks like this. So continuous and decreasing and positive. And say this x value is n, this is n plus 1, this is n plus 2, capital N, and so on, n plus 3. Then over here, we're coming down to the end, we have n minus 1, little n minus 1, little n, and n plus 1. So then, if we look at these rectangles, these rectangles all have a width of 1. They're determined by this height, which I'll talk about just a second. Yeah, let's keep it going down, just so it's a little easier to see what's happening. Instead of leveling off quite so much, just keep it going down at a steeper angle. And then, lastly, this one. Well, if you'll note, all of these values, are the function values of f. So this is f of capital N. This is f of n plus 1. But it's also, of course, a sub capital N, a sub n plus 1. And note, since the height of that is a sub n, the area inside here also has to be a sub n, because area of a rectangle is height times base, and the base is just 1, so 1 times a sub n. So this is a sub n plus 1, a sub n plus 2. And that's helpful because we can now compare with the integral, because the integral is the area underneath here. So if we look at the integral from capital N to little n plus 1, this would be a sub n little n minus 1 and a sub n. The integral from capital N up to little n plus 1 of f of x dx has to be less than or equal to the sum of all those rectangles area. So this is less than or equal to a1 plus a2 plus a3 plus dot 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 a sub n plus a sub n plus 1 plus a sub n plus 2 plus dot 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 a sub n minus 1 plus a sub n. That's certainly true. Then, if we draw them this way, our rectangles this way, well, it just shifts the rectangles over 1. These are now underestimates. So if I do a similar integral, if I do the integral from capital N to little n, so from up to here, well then, if I look at that of f of x dx, that has to be greater than or equal to, well, from here to here, that would be this a sub n plus 1 plus a sub n plus 2 plus dot 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 all the way out to, I could include this one as well, but I want to use the same stopping points, so let's see here. Out to a sub n. And just so we have the same sum in the middle, you can add that a sub capital N to both sides. So a sub n, a sub capital N, plus a sub capital N plus 1, plus a sub capital N plus 2, plus dot dot dot, plus a sub little n is less than or equal to integral capital N to little n of f of x dx plus a sub capital N. And now you have both an upper bound and a lower bound. The integral from capital N to n plus 1 of f of x dx is less than or equal to a sub n plus a sub n plus 1 all the way up to a sub little n. And that's also less than or equal to the integral from big N to little n of f of x dx plus a sub capital N. Well, that means you bounded it both above and below by the integral, and above by the integral and some finite number, but still. Well, that means then we can take the limit as n goes to infinity. Little n goes to infinity of all three, and that means we have, well, integral n to infinity f of x dx less than or equal to the series from n equal capital N to infinity of a sub n less than or equal to the integral from capital N to infinity of f of x dx plus dx, forgot the dx, plus a sub n. Well, that means then, if integral of n to infinity of f of x dx is finite, so is the series, because it bounds it from above. And if it's infinite, so is the series, because it's also bounded from below. Because of that pretty simple argument, that means if the integral converges, so does the series. If the integral diverges, so does the series. So it's a nice little test. Let's do some exercises. Alright, first off, we're going to look at one of the more important set of functions for comparisons. We're going to look at the p-series. So here we're looking at the sum from n equal 1 up to infinity of 1 over n to the p. And these don't always converge. This is, p is some number. So when does it converge? Well, if we do the integral test, because certainly it's positive and decreasing for n1 to infinity, it does need to be above 1, because if n equals 0 would be a problem just because it would be undefined at a point. But in any case, let's go ahead and do this. If you look at the integral from 1 to infinity of 1 over x to the p dx, well, this is 1 to infinity of, let's see, it's x to the negative p, so plus 1 over 1 minus p. Well, then you can see what you need. If p equals 1, it's undefined. Alright. If p is greater than 1, well, then this will be a negative number. The bottom will be negative as well, but because it'll be a negative number, you plug in the limit as n goes to infinity, x to a negative exponent will go to 0. So p greater than 1 converges. I mean, if you don't see that, just take a, say, 3. X to the 1 minus 3, if you're thinking of the limit as x goes to infinity of that. That's x to the negative 2, or 1 over x squared. Limit as n goes to infinity. X goes to infinity. And that's just 0. So that would converge in that case. If p is less than 1, however, so for example, if p was 0, then you'd have x to the 1, limit as x goes to infinity. I'm not bothering with the bottom, because the bottom would just be a constant. You know, 1 minus 0 would just be 1. 1 minus 3 would just be negative 2. It's the function part that we're worried about, so that's what I'm experimenting with. If you take x to infinity, that's just going to go to infinity. So, diverges. So, for p-series converge if p is greater than 1. And remember, this is 1 over x to the p. So, or 1 over n to the p. And I suppose that's actually, we can actually integrate it for 1 because it diverges. So let's actually look at that case. I forgot. Yeah, the power rule doesn't actually apply in that case. If we're doing that, though, 1 to infinity of 1 over x dx, my bad. Integral of 1 over x is, of course, natural log x, and that's 1 to infinity. Well, this diverges because as you plug infinity into ln of x, it goes to infinity. So it still diverges. Just by a different argument than that. So the p-series converges if p is greater than 1. We'll use that. Remember that for later. Alright then. Series converge or diverge. First off, you should make sure the sequence actually goes to 0, Because if it doesn't, you should just use the nth term test and say it diverges. But ln of n over n will go to 0 as n goes to infinity, so it does have the possibility of convergence. I think we can just integrate that. If we look at 2 to infinity of ln x over x dx, you can just use u equal ln x. So du is 1 over x dx, which is exactly what I have. So it's the integral from, I mean, I guess I could convert the limits. Ln of 2 to infinity of u du. So that is ln of 2 to infinity of 1/2 u squared. And that is definitely diverging. Because as you take u to infinity, this goes to infinity, and ln of 2 isn't going to cancel anything out. So our next problem down here, just based on having a bigger exponential function on the top than on the bottom, I'm not convinced this would actually go to 0 at all. So let's actually do a little test here. Divide top and bottom by 4 to the n. That just sequence would be 5 over 4 to the n over 1 plus 3 over 4 to the n, which would go to infinity over 1. So that goes to infinity, so we can just say that diverges by nth term test for divergence, because it didn't, the sequence didn't go to 0. The series can't converge. I think the trick here is that if you look at ln of 2, I think that's less than 1. Yeah, it's about 0.69. So when you take higher and higher powers on it, the bottom is going to get tinier and tinier, which means the sequence itself isn't going to converge. So if we look at the limit as n goes to infinity of 1 over ln of 2 to the n, this is going to go to infinity, so series diverges by the nth term test for divergence. But if we look at the next problem, which is very similar, ln of 3 to the n, ln of 3 is bigger than 1, because 3 is bigger than e. So this is actually decreasing, is a positive decreasing function. So for this one, it could converge. It is basically an exponential function. This one, I think I am going to integrate it. So we're looking at integral 1 to infinity, 1 over ln of 3 to the x dx. I think we can just integrate this. That's ln of 3 to the negative x dx. Integrate that, you will get 1 to infinity of ln of 3 to the negative x times ln of 3 ln of 3, I should say. Yeah, because derivative of a to the x. Oh, no. Integral of a to the x is a to the x over ln of a. So this is 1 to infinity of ln of 3 to the negative x. I still got to deal with the negative, but over ln of 3. And then times the negative, because if I let u equal the exponent, I'll get du is negative dx. So if we look at this, then, you know, all of this is just a constant, negative 1 over ln of 3 times the limit as x goes to infinity of ln of 3. Oh, I don't need the dx anymore. Ln of 3 to the negative x minus ln of 3 to the negative 1 well, this will go to 0. So, because of that, this thing will converge. So, converges by integral test. This integral converged, so does the series. Note, the sum doesn't necessarily have to equal this. It doesn't tell you the sum of the series, it just tells you whether it converges or not. Alright, last of our convergence or divergence problems. Let's look at this. We have 8 inverse tangent of n over 1 plus n squared. This is a uniformly positive function. As for whether it's uniformly decreasing or not, I guess we can look at this graph. That's probably the easiest way to evaluate that. Eight inverse tangent of x divided by 1 plus x squared. Seems like it will be. I don't really care about negative values, so I guess I'll go 0 to 50. I'd call that decreasing. Yeah. So because of that, this, inverse tangent actually just approaches pi over 2. Just so, even though it might increase initially, this is going to win out. The bottom's going to win out, so that's why. With that in mind, we can apply the integral test then, because we are positive and decreasing. Not actually sure if it would be from 1 to infinity, but certainly it would be some tail of that. So if you wanted to, you could split up like 2 to infinity or something like that. That might be worth it, but regardless, I'm not going to be undefined at this bound anyway, so it shouldn't affect the convergence of the integral. So integral of 8 inverse tangent of n over 1 plus n squared. What we're going to do here is just a simple a simple substitution, I think, because u equal inverse tangent of x, its derivative is 1 over 1 plus x squared dx. So this is just going to be 8 integral 1 to infinity. I guess I can make that work. Tangent inverse of 1 is pi over 4. And tangent inverse of infinity is, well, it actually goes to the limit as x approaches infinity. That's kind of rough. But the limit as x approaches infinity of tangent inverse is pi over 2. So, I guess that would be true, though, considering how we're doing the limits here. So 8, and this would be u du. Yeah. So this would become 8 integral 1/2 u squared from pi over 4 to pi over 2. You could also do the full press of doing this. Limit as b goes to infinity of 1 to b of 8 u du. And then, you get, what, 4 u squared. And then substitute back, 4 inverse tangent of x squared. And then you'd be going from 1 to b of limit as b goes to infinity. And that would come out with the same thing, though. The point is, this is going to be a finite value, so this converges. So does series. The last thing in this section we're going to talk about is estimating the error, or the remainder, of doing one of these. So let's look at a slide real quick. So the remainder in the integral tests, the difference between the actual sum and the s sub n, the nth partial sum, can be bounded by the integral. The integral from n plus 1 to infinity is going to be less than or equal to the remainder. The integral from n to infinity is going to be greater than or equal to the remainder. So just because of that, you can actually use this to solve for what n has to be. In this problem, we do have a continuous decreasing function, so we can use the integral test. It's good because we have to use our estimate. Our estimate says the integral, our remainder, r sub n, which is s minus s sub n, is less than or equal to the integral from n to infinity of our 1 over x squared plus 4. We want that to be less than 0.1. So we do our integration. This is it's 1/2 inverse tangent of x over 2. If you look up the formula for 1 over x squared plus a squared. So this is going to be n to infinity. 1 over 2 inverse tangent of x over 2. Now as x goes to infinity, the inside of the inverse tangent goes to infinity. Inverse tangent will go to pi over 2. So this is 1/2 times pi over 2 minus 1/2 times inverse tangent of n over 2. So less than 0.1. Do some solving. We take this over to the other side. So negative 1/2 inverse tangent n over 2 less than negative pi over 4 plus 0.1. Multiply off the negative 2, inverse tangent n over 2 is greater than, because I multiplied by a negative, pi over 2, because we multiplied by 2, plus 0.2. Take a tangent of both sides. It's somewhat suspect about what that would do to the inequality, but I'm not really worried about it just because I know n has to be greater than some bound for this to happen. So I'm just going to keep it as greater. Tangent of pi over 2 plus 0.2. And then multiply off the 2. N is greater than 2. Tangent. Oh, that should be a minus right there. Yeah, because we multiplied by a negative, that should be a minus. 2 tangent pi over 2 minus 0.2. Let's plug that into the calculator, see what we get. Alright, 2 tangent of pi over 2 plus minus 0.2. Not graph. Dangnabbit. There we go. Alright, so that's about 9.87. Of course, we want to round up to have enough margin, so n is greater than 10. And I guess it could include it since it just has to be greater than that 9.6 value. So n is greater than or equal to 10. So then, we want to estimate up to that, so then we just want to do a sum from n equal 1 up to 10 of 1 over n squared plus 4. You can do this in your calculator, although it's pretty complicated in the TI-83. In the TI-84, I believe it's actually just the bottom function in the math menu. But I'll do it in here. To do it in the TI-83, you have to go into the list, go over to ops, and go down here to sequence. So we're going to build this sequence. You have to tell it your formula, so 1 divided by x squared plus 4. What the variable in your formula is, which is x, your starting place, which is 1, your ending index, which is 10. So that generates the sequence. You see the first one would be 0.2 because it would be 1 over 5. And then you want to take the sum of that. So you go back into the list menu, go to sum. Actually, let me get my previous answer here so I can add on to it. There we go. Insert, second list, our sum, and then close it. So we get approximately 0.57. And that is our answer. That's within 0.1. That'll be it for this video. Next time we'll look at the comparison tests. Have a great day. Stay safe out there.